Heath Cosin.
I'm Ryan Ness.
I'm Jess Dory.
And I'm Troy Holland. And we are a student group from the Oregon Institute of Technology in Portland, Oregon. And today we're going to talk to you a little bit about a wind turbine that we designed and built. This project was for a senior level electrical engineering power conversion class. So the goal of the project was to take a prime energy source and move it through some power electronics so we might be able to store some of that energy and do something with it. So we decided to do a micro wind turbine for use in developing countries, and we're going to talk through the design, fabrication of that project. We'll start with that.
All right, so I'm going to talk a little bit about the goals of the project here. The main goal of the project is to design a renewable energy power system for a developing country that rely on expensive diesel fuel for their electricity needs. We wanted to make the design simple, so it could be easily built by people who didn't know anything necessarily about renewable energy or power or anything like that. So
here we have a photo illustrating the simple design of the turbine. The blades and the hub make up the rotor, or the portion that rotates due to the force of the wind, the generator, the boom, and the vane. In this case, the rotor has been built from 4-inch PVC pipe. The hub, the boom, and the vane were from recycled steel, and the generator is a permanent magnet motor that was salvaged from a treadmill.
next we're going to talk about some of the different components of the project, and Heath is going to talk about the blade design.
Hi, I'm Heath. I'm just going to talk about how we designed the blades for the turbines. Obviously, like Ryan said, we chose PVC just due to its availability in most countries. And what we needed to do is get the right angle on the blades so that we would get the output we desired from the generator. Luckily, somebody already made the function to get our build angle, which is this angle phi here. If this red circle is our PVC pipe, and this angle obviously is higher towards the hub, and as you come away from the hub, that angle decreases down to close to zero towards the tips. And like I said, the function was we already had to map that function to get this angle. And the function, basically, the inputs are your tip speed ratio, the optimal build angle, which is about 16 degrees, and the radius of the wind turbine blades. And the tip speed ratio, that's just the ratio of the tip speed of the blade to the wind speed. And we were going for a higher number because we wanted to maximize the efficiency. We weren't really worried about torque because we're not pumping water. We're producing electricity to charge a battery. And then to find this length, which you can see here, is we use this equation, which basically takes this angle and then finds the length along the pipe. And obviously you can tell towards the hub, it's higher, it's about 74 degrees, and then when we get down to the tip, it's about 4 degrees, so you have a smaller length. And you can see that in the actual blade. Here, it's about, well, it should be 74 degrees, and then as we come out, that angle is slowly decreasing down to 4 degrees at the tip. And that's basically how we designed the blades for the turbine. So, taking the lengths that we got from the computer program we made, we basically made a template, and every 5 centimeters we have our length. And you can see the template here, how it starts. The length is longer, and then it slowly comes down as our angle decreases. And we transferred the template onto the pipe, laid it down, and then drew out the cut line. Cut it on the bandsaw. You could use a hand saw, jigsaw, or even circular saw if you had to.
next we're going to do a live demo of a simulated wind inside the lab here. We set up 2 industrial floor fans to blow wind on our wind turbine. And here we're going to hook it up. We'll blow about 4.5 meters per second, between 4 and 4.5 meters per second. So Heath, hit the fans. We have an anemometer here for the wind speed. The reading is in meters per second. So we're getting almost 5 meters per second here from these fans. So now we're going to go back to the wind turbine.
I was just going to briefly discuss the flow of energy through the system. The kinetic energy in the wind travels through the blades. The blades, which are hooked to the rotor, convert the kinetic energy to mechanical energy, which is then fed in through the generator. The generator converts the mechanical energy into electrical energy, which is then fed into the power electronics, where it is conditioned and then fed into the battery for storage and later usage.
Once we assembled and tested the machine, we made a series of voltage and current measurements at different wind speeds in order to characterize the power output of the turbine. The amount of power available in the wind varies with the cube of the wind speed. In practice, we need to design our power electronics to take advantage of the light winds that blow most of the time, instead of the strong winds that only blow once in a while.
Here you can see the wind is coming into the blades and into the generator, which converts it to electrical energy. And then that is fed into a boost converter. Our voltage range was from between 1 volt and 10 volts, so we wanted to boost that up to about 16 volts so that we could feed it into a battery. The boost converter boosts our variable voltage input up to about 16 volts and feeds that into a regulator, which then regulates that voltage better into about around about 15 volts, which is then fed into a charge controller, which varies the current going into the battery based on the voltage level between the battery and the output of the regulator. And this is our input voltage going into the circuit. This is the boost converter, and this is the voltage regulator.
And here you can see we have about 14 volts, which should be sufficient to charge a battery.
Here we've included a bill of materials. You'll notice the hardware components are in blue, the power electronics components are in white, so the total cost was just over $26 US. Again, one of the design features was to make the design as inexpensive to construct as possible.
And that concludes the design, implementation, and demonstration of the wind turbine that we built for the Power Electronics Conversion class at the Oregon Institute of Technology at the Portland campus. We'd like to thank both the program director, Robert Bass, and professor for this course, Kurt Ebenson, for their inspiration and help in these courses.
I'm here to laugh, love, fucking drink liquor, and help the damn revolution come quicker. Laugh, love.
I'm feeling frisky. I'm feeling so frisky.